So, we have been asked to implement section 1.3.1 in the textbook, and the general idea here is that there are two fair dice. Let's write that down. Two fair dice, and someone else has rolled them for us and told us that the sum of the scores is 9. So we say sum of scores is 9. What we want to find out is the posterior probability of the dice scores, i.e. if we define the sum to be 9, t as a variable, t is equal to 9, and each of the dice scores to be SA and SB, so there are two die, then we want to know what's the probability of SA and SB given t is equal to 9. Okay, let's go do that using programming techniques. First we need to find the function for our MATLAB program, and that has to match my file name, so I'll call that 2dice. And now I want to, well, it's called my 2dice, let's be personal. And now I want to import everything in the BRML toolbox. So do make sure you have the Bayesian reasoning machine learning toolbox attached to your MATLAB. How to do so has been explained in another video, which has been attached to this video, so do make sure you have it. So we import brml.star. Next, we have to define our variables. And so I'm going to make a good comment to be a good programmer. Arbitrary variable numbering, I'm going to call it. Because I could order them in any order I wanted to, as long as I make sure my first index is 1, because that's how MATLAB starts. So SA was my first dice variable. I'll always set that to the index 1. SB can be 2, and T will naturally be equal to 3. T being the sum of SA and SB, or the random variable representing that sum. Next, I need to define my variable names. Variable names. And let's start with SA. So variable SA.name is equal to SA. I also want to define its domain. So variable SA.domain. So domain represents the values SA can take. So it can either be 1, 2, as you can guess, next is 3. If I can type 4, 5, and like any normal dice, it ends at 6. So it can take only one of these 6 values. That's the domain of SA. SB has exactly the same domain. So we're going to copy paste that, Control C, Control V, and put in SB everywhere here. I've got a small typo. I should not have written variables. I should have written variable. Better. SB. Variable SB. And that's all good. Next, we have to define the variable name for T. I'm not actually going to bother defining its domain because I never explicitly use it in finding the posterior. So we're just going to do variable T dot name equals T, and that's that. Next, I have to define my model. What do I mean by model? Model is essentially the joint distribution of all my variables. So model is the probability of T, SA, and SB, which I can decompose into a product of potentials, i.e. terms independent of one another, as using the law of total probability. So in general, this would be probability of T given SA, SB, times the probability of SA given SB, times the probability of SB. And each of these terms is a potential, which I can fully define and then multiply together to get my overall model, the joint probability. However, in this case, we are lucky. We know that the dice are independent of one another, i.e. the score of SA does not at all matter on SB. So this probability distribution can be simplified to not even include the given probability on SB because it is independent. So now we just have to define this probability distribution fully, this probability distribution fully, and this given probability distribution fully to be able to define our model. So let's go do that. Let's define these potentials, starting with SA. So potential of SA is equal to an array, and I need to define what variables it includes. So dot variables is equal to only SA in this case. Now, I know because it's a dice and it's a fair dice, there's only 1/6 chance of having any of its 6 values. So I'm just going to use a for loop to populate the table for this potential. So for I is equal to 1 to 6, we're going to say the potential of SA dot table, and we're going to index into position I, which iterates from 1 to 6. And for each of these positions, we know the probability is 1 over 6. And we have to do this clunky thing in MATLAB. We have to end the for loop. Next, we have to do the same thing for SB. So I'm going to do my favorite trick: Control C, Control V, and just change all these to B. There must be an easy way of replacing, but I'm going to do this manually. SB. Next, there's only one more potential left to define, and that's the potential for T. So I'm going to call it pot T, though in reality it's going to be modeling this distribution, P of T given SA and SB. We are shown in section 1.3.1 that this is actually equal to simply the indicator function, which I'm going to use letter I to represent, of T is equal to SA plus SB. As a reminder, I is equal to indicator function. So what this means is that if the condition T is equal to SA plus SB is true, so i.e. we choose the values of T, SA and SB to make this condition true, then this function I of T is equal to SA plus SB will return 1. If it is not true, it will return 0. And this makes complete intuitive sense. If we know the individual scores SA and SB, because this is a given probability, then the probability T is equal to the sum. If T represents a sum, the probability T is equal to SA plus SB will only be 1 if T is equal to SA plus SB. So that makes complete intuitive sense and complete logical sense that you can only have the probabilities 0 or 1 for T if we know SA and SB. For example, if SA is 3, SB is 2, and we are looking at the probability T is equal to 4, we know 3 plus 2 is 5, so the probability T is equal to 4 is 0. Probability T is equal to 5 is 1. And that's why we can use a simple indicator function. Okay, so let's define the potential. So potential of T is an array. Potential of T dot variables this time are 3 variables, T, SA, SB. So T, SA, SB. And now we're going to use a triple nested for loop to iterate through the different values of T, SA, and SB. So I'm going to use I to iterate through the values T can hold. Oops. And we know T can hold values between 2 and 12, but I'm going to start at 1 because I may as well populate that index. Next we're going to use the letter J to iterate through the values SA can hold. So for J is equal to 1 to 6, and letter K to iterate through the values SB can hold, 1 to 6. Now we're going to implement the indicator function, just using a basic if statement. So I'll say if J plus K, i.e. the sum of SA and SB, is equal to the value T is holding, which is I, then I'm going to set my value to be equal to 1, i.e. return true in a way. Let's create some space. However, if this is not the case, so else, I'm going to say the value is equal to 0. So the probability of T being the value I is claiming it to be is equal to 0 if J plus K is not equal to I, because it can only ever equal J plus K. Okay, now we do this clunky thing of ending the if statement, and we'll always now populate our table. So potential of T dot table, and we want to look at position ijk, and through these nested for loops we'll be able to iterate through all the values of I, j, and k and populate the entire table and send it to val, which is either 1 or 0. The probabilities can only ever be 1 or 0 for T given SA and SB. Now we have to end all our for loops. End. Next thing we want to do is define our joint distribution, which is our model, joint distribution, which is the model we defined as the product of our potentials over here. So we can do that quite simply in MATLAB. We can just use the BRML toolbox function multipots, which will multiply our potentials for us. So I'm just going to call this joint pot is equal to multpots. So multiply potentials. The ones I want to multiply are defined by pot. Excellent. Now we can actually calculate our posterior. So what we want to display is the probability of SA and SB given t is equal to 9, i.e. the joint probability of SA and SB, the scores, given we've observed that the total is 9. The way we can do that is use the function display table. So disp table, use the function contpot, so conditional potential, to say what we're conditioning on or to create this conditional distribution. Contpot, and setPot to actually set the value to t equals 9. SetPot, and that's inside our model joint pot. And we set t is equal to 9. Close this. We want to observe SA and SB as a joint distribution. Close this, and for all the variables. Variable. And that looks reasonable to me. And let's wait for the red line to disappear, which it did. Excellent. So if you actually look at the section 1.3.1 in the textbook, you'll observe they found there were only 4 non-zero joint probabilities for SA and SB given t is equal to 9. And each of those probabilities were actually 1/4, i.e. equiprobable. So let's see if our program gives the same answer. So I'm going to run it over here. I'm going to say my 2 dice and run. Excellent. So we've got the answers. Scroll up a bit. I'll expand this so we can see them all at once. Quite a few. So over here you can see that probability of SA and SB given t is equal to 9 is 0 pretty much everywhere, apart from when SA is equal to 6 and SB is equal to 3. That has 25% chance. If you scroll down, SA equal 5, SB equal to 4, then reverse 4 and 5, and finally 3 and 6. This also makes complete intuitive sense that each probability is 25% for every combination that can give 9, because there's no reason, based on observing the total score, that any one combination is more likely than the other, because the setup is completely symmetrical for SA and SB. So there we are. We've implemented the example using MATLAB and the BRML toolbox. And that is that.